me about some stuff that they have done with Wikipedia data. And before he begins, I would like to just mention one thing that actually last Friday I sent the announcement of the seminar, and a couple of hours later people from a radio in Mallorca got in contact with me because they wanted to do an interview to Paolo, and actually they have done the interview to you right in Tuesday, and I think the interview is very short and very generic, but has been recorded, and I guess it could be available for those. I don't know. Anyway,
I will continue the interview. Yeah?
So please.
Okay, thanks for coming. First of all, I don't have to read you the title of this research. This research was entirely done here at IFISC. Before beginning, I'd like to thank, first of all, Arkis Tamampokis, that is the guy from Lesbo Island in Greece, that collaborated in the massive computational work to perform this research. After that, of course, Victor and Emilio supervised this research in a brilliant way. And, I'd like to stress that it's not a trivial thing. You go to your boss and you say, look, I'd like to research the structure of meaning. And, the usual answer would be the meaning of what? Or, I don't know, or did you drink this morning? Or whatever. Well, they say just yes. Let's go. And, I think something like that can happen only here at the IFISC. I'm infinitely grateful for that. All right. I think here we have a very large audience, so we're not going to speak too much technically. Most of you, some of you, are used to consider language as a physical system. Some of you maybe are doubtful about that. Some of you maybe think this is really something out of space. Well, let's begin with talking about language. What is language? Actually, it was around 1 month ago, I was talking with a friend of mine, a guitar player, about this thing, about the semantic space. And he told me, well, Paolo, this is very cool, it's very interesting, but where is the semantic space? Yeah, that's good. Yeah, that's true. I mean, we are measuring it, and where is it? Well, the answer is it is in your head. I mean, it's in your head. It's language is a collective phenomenon. This is the reason we're here and studying it here. Basically, language cannot evolve with just one person. You need at least 2 persons to develop a language. And language, what is language? I mean, neo-positivist physicists say that it is to transmit information. I prefer the exception in which you consider language as a transmission of orders. I mean, words are order words. This is the post-structuralistic interpretation coming out from the 60s, from Derrida, from Lacan. So basically, we create between each other this collective phenomena that is language, and we use it to organize each other. So we use this space to organize ourselves. So you have a system that is a social system that creates a kind of shared space that is language, through which we give orders to people to organize. And well, after this, language for linguists is divided more or less in syntactics, semantics, and pragmatics. Now, the first two, syntactics and semantics, are the ones that are considered in physics to work on. Network theory was used to study syntactic space, that is the space of grammar and syntax relations, syntactic relations. Semantics is the part of linguistics that deals with meaning. So the meaning, but as we told before, the meaning of what? So let's say an apple. But you got an idea of what an apple is? You know, Emilio? What is an apple?
It's a computer, isn't it?
That's a good answer. I prefer assemblages of computer, but Emilio, imagine you are not a native English speaker. It's not that difficult. What you do to see, you find this word, apple, you want to see the meaning of it. What you do?
Looking in a dictionary.
Well, and here we are. I underlined that it was a voluntary test that we didn't arrange before. So, in a dictionary meaning, you find apple, and you don't find a computer. You find that is around fruit, whatever, blah blah blah. You can read that and you see, okay, the apple is a fruit, it's round, it's a tree, and whatever. But if you're a physicist, you won't see it in a more naive way. So, what is an apple? And if you see this, the first thing, maybe the second thing you can think about, it's a collection of words. So, this is, I want to make you notice this, because this is our first definition. We are looking for an operative definition of meaning, and this is our first definition of meaning. The meaning of a word is a collection of words. Well, this was noticed by Derrida in the 60s, but you can already understand that if a word is a collection of words, and each of those words is a collection of other words, and so on, what it comes out is a structure that has the shape of a network, what they used to call a rhizome. Now, as Emilio pointed out before, well, Apple is also a computer. In the sense, the dictionary meaning is has been objected that is not the semantic meaning, but is the way we describe the language used. So apple is a noun, the plural is apples, it is a fruit, etc., etc. For what we know, an apple can be a representation of New York, can be a famous computer, or can be the apple of sin, for instance. Yeah? And can be also, since we have physicists, the apple that nearly broke the head of Newton. In a sense, that from the dictionary meaning, I want to introduce you to a meaning, a definition of meaning that is more semantics, that is the encyclopedic meaning. This is the definition of apple in the actual Wikipedia. We're talking about 17 pages of descriptions. Because apple is not just an apple, like a pipe is not just a pipe, we all know it. For instance, if I can find the arrow. Well, there is not the arrow. Well, we don't have the arrow. Well, I mean, it's not really compulsory. It was just to magnify some. I wanted the arrow, but well, it's fine. It's fine. I want just to point out, for instance, here we got the botanic, the scientific definition of apple. That is a fruit. It's taxonomic classification. Here we have the botanical information of apple. And here, for instance, we have all the cultural information, I mean, some of the cultural information about the apple. We have German paganism, we have apples in Greece, or we have apple in the Garden of Eden, and so on with all the healthy stuff, the pollination. So basically, this was Umberto Eco that pointed out that the meaning of a word can be defined in an encyclopedic acception as a collection of interpretants that circumscribe the meaning of that word without touching it. Interpretants, okay, Umberto Eco talked about semiotics, so science in general. Here, those interpretants are other words. For instance, let's see it in this way. This is the same page. I removed the articles, the punctuation, and I put just the words describing the word apple. Their size is proportional to their frequency in the Wikipedia page. So we can see it here that the meaning of a word assumes a characteristic that allows a formal interpretation, especially in the sense of metapopulation system. In a sense, the meaning of a word is a population of other words that circumscribe that meaning, and if you go to count, to take many pages of an encyclopedia, you have a metapopulation system where every population is a collection of words, of different words with different frequencies. So the parallel I want to point out is the parallel with the metapopulation system. This is a biological system. We can consider this space of meaning, so the semantic space, as a collection of populations where the species are, the different species are the words, the different vocabulary used. And every population, so every meaning, is characterized by a frequency distribution of words and by its size. Well, if you agree with that, I can go on. And let's say, okay, we formalized the semantic space in this way. What we want to do is to understand the dynamics of this semantic space. In the sense, those populations are pages of an encyclopedia. Pages of an encyclopedia, basically, they grow in time, they get birth, they die. They're like really biological populations, and they interact by a phenomenon that is very similar to migration or inheritance of attributes. So in a sense, if I want, I'm writing a page and I want to write something, add something, for instance, from the apple, add something that is related to New York, I will probably go to the page of New York and read there and grab some of the words and put it in my page. This is a phenomenon that is very similar to migration or inheritance. And this is to go on with a parallel with biological species. We will see that this parallel has empirical evidences. So what we want to see is the dynamics of migration between those populations. And we do it with a concept of semantic flow. I'm not going through the details that you can find at this reference of the semantic flow, but let's say that imagine we have two pages that have some elements in common. Then we can guess there was an interaction or a migration or inheritance. We can translate, of course, this sketch on this drawing on a probabilistic plane, so that we have the first page described by a probability distribution P, and the second page by a probability distribution Q, with some common words, so some shared attributes. Well, I'm not going into details, just to show you the measure. I used to measure the semantic flow between the different pages is this distance that is symmetric, forms a symmetric, that is based on the Jensen-Shannon divergence that we have at the numerator, and at the denominator we have a normalizing factor to allow to apply this measure to a system of many populations. The measures are the measure considers the probability distributions of the pages and their size. So also the fact that there are different sizes is considered. And this H is the Shannon entropy. So we are at the level of descriptions of information theory. After that, we want not only to measure the amount of this semantic flow, but also its direction. To measure the direction, we're shifting from semantics to biology to geography, social geography. We use concepts of geographical segregation. Now, if you have a population that is geographically segregated, what does it mean? Imagine Jews in a ghetto, or Mallorquin people in Mallorca. They, for instance, they are segregated toward a lot of attributes. What is the difference? If you go to Spain, you find that the attributes of people are more or less mixed. In a sense, if you suppose that here you have a measure of some attributes that can be some social indicators, your age, the color of your skin, or the color of your eyes, or let's say that if you find a uniform distribution, it means that the population is not segregated. You have a lot of influences from around, and this mixes up everything, and you result with a uniform distribution, more or less. If you are segregated, the distribution comes out to be peaked. So, in this way, since we know that Shannon entropy is in this way, okay, if we have, let's say, if we know there was a flow of information from here to there, and we know that here we have a segregated population, and here it's not segregated, we can infer a flow of the information from the segregated one to the not segregated one, to the open one. And you can measure this considering basically the entropies of those distributions, the quantified inequalities of the distributions, with the contribution also of the percentage of the attributes shared. Okay, also here I don't want to go in technical details because I'm going to bother you, but you can find a reference in the same paper before. Just to know that now we have the instruments to analyze these metapopulation systems that are the pages of Wikipedia. To show you some example of the fact that this method is efficacious, here we have 85 pages, more or less, divided in 14 categories. And we apply those algorithms to find out the migration or the semantic flows between the different pages. It is interesting to notice that the network now is given with is drawn with Spring embedding algorithm. In a sense, it's really automatic, and we can see that the method catches all the categories in a very exact way. So here we have animals, medicine, biology, in nature, here we have religion, here politics, philosophy, physics, literature, whatever. Yep. So this is just to show you that it works. Here we have another example. I think it's fun. Yeah. Let me explain to you. Those are always pages of Wikipedia. On the left we have international politics. Those guys probably you don't know them, but they are very, very famous bosses of Sicilian mafia. And as we see, the point of between a centrality of the network is our, we hope, former in the future prime minister. So, are you convinced about the method? we could use it also in a trial.
I think that this method depends on the encyclopedia too.
Well, this method as put like that, it doesn't even depend on the encyclopedia. We also applied it to genetical systems, and it's.
At the beginning, every article approach belongs to some encyclopedia.
Sorry?
I mean, if you, I don't know if I understood your method, but when you come to a page in a particular encyclopedia, and then you try to relate different pages.
Yeah.
But what I mean, if you go to a different encyclopedia, it's going to give you different results? Or?
Well, let's see before the results. I think that we didn't try to different encyclopedias, but the results are quite strong, and I think they are quite general. And it depends on the as we will see, on the content, on the content-based network concept. But we will see it later.
You put arrows here. It's just, I mean, do they are really in that direction or
No, the arrows are comes from the algorithm of directionality I showed before.
So Angela Merkel is dictating the other what they have to do.
Let's say the page of Angela Merkel is, well, the other pages are inheriting attributes from the Angela Merkel one, from this analysis.
But that's in time? Or,
no, this is just pages, actual pages of...
stationary, so how do you understand the flow of the words?
Sorry?
So you say that's the flow of words from one page to the other?
Oh, this
or
is
the word is going from one to the other, or vice versa?
No, this is the what the direction. The semantic flow is basically a measurement of correlations. So basically, when you see that there are common words between pages, you say there is a flow, a semantic flow. The directionality that is comes out from these algorithms.
Yeah, but can you explain that? I mean, I
Yes.
don't understand it.
Okay, I can explain it again. The algorithm itself,
No, I mean,
or
I
this.
understood what you explained, but I don't relate that to what you are actually doing. I mean,
Okay, what I'm doing, well, let's say that we have two pages. One described by a probability distribution P, and the other by probability distribution Q. One of size M1, one of size M2. Then we calculate the distance with this formula.
That's the overlap of the two histograms, essentially.
More or less. It's a bit more complicated because it considers also, this formula considers also the outer part. It's not only the overlap. And this is the formula to assign the directionality. So P is the probability distribution of the first page, Q of the second, and this is basically the concentration of shared elements between the two pages. So if, let's say, to see if the shared elements are a relevant part of the page or not. This is a factor that goes to the denominator of the. This is basically an index of segregation, and we just keep the difference, and we just consider the sign.
But can you explain heuristically? Say you take the Angela Merkel and the Berlusconi page.
Yeah.
Why do you get an arrow that goes from Merkel to
Oh,
Berlusconi?
that
I mean, what
is
the page
that is to see what they share. I mean, this comes out from different pages. It changes between Angela Merkel and Berlusconi. I suppose there is these things of the international politics in common. So probably the directionality comes out from the fact that the shared words are more segregated. So the political words are more segregated in Angela Merkel, while are more general in Berlusconi.
I think the heuristic is quite easy. So you go to a place in China and everybody is Chinese, then you go to a place, say in Africa, and everybody is black, and then you go to and then you go to a place like New York or London, you see white men, black men, Chinese, all of this. Then can you guess where has been the immigration flow? From the place where everything is more mixed to the others, or from the place where everything is segregated, unique, towards the mixed one? The assumption we make here is that the flow is from the most, say, uniform populations towards the mixed ones. This is the assumption. We can think on the situation in which this doesn't work, but the general trend, I think this is correct. Probably the page by Berlusconi contains elements of politics, but also elements from from many things. Probably the one by Angela Merkel is much more segregated than politics. And this is the heuristic ideas behind the method.
But we can talk about this later in details.
Are you restricted to the English version of the Wikipedia?
This is we didn't write yet, but I'm going to analyze the English version. So, just as first conclusion, before going on, we gave a physical formalization of the concept of meaning, a representation of semantic space as a metapopulation system, and this measured directional semantic flow. So this was the break for the questions, but we already did it. So now we're going to see the topological analysis of.
So again, you're summarizing. Can you summarize again, which is the physical formalization of meaning?
As the meaning of a word defined in a dictionary encyclopedic acception as a collection of interpretants that are the words contained in a hypothetical encyclopedia to describe the meaning of that word.
Yeah, but that has nothing to do with the concept of meaning in the social literature.
In the social literature? What do you mean?
Well, there is a famous paper entitled "The Meaning of Meaning." And by meaning, not the fact, but how you interpret the fact. That's meaning for you. But that has nothing to do
that's. I mean, there are a lot of interpretation of meaning that are very ontologic, in my opinion, and some that are right to be innatist. I'm more on this point of view that is very structural, and I think it is efficacious apart from the aesthetic to work on it, because when you say something is innate, then how can you work on that? You have to talk with God, and it's difficult for many of us. We are going to see the topological analysis of the semantic space, and then introduction of a model that will restrain this parallel between the semantic space and a biological system. As we told before, we're going to analyze Wikipedia. Wikipedia is something similar to this hypothetical encyclopedia Umberto Eco was talking about, because all the encyclopedias were just books, and every 5-10 years were renewed. Well, the Wikipedia is an open encyclopedia. It grows in time for the number of pages and the size of the pages. It really looks like a living organism. We downloaded a complete snapshot of 2008 of Wikipedia that consists in around 2 million pages. With this number, I cannot tell words. And this is just the statistical distribution of the page size. Just a break to say how we treated the data set. We removed the redirection pages, first of all. And we worked on the content of the pages. In particular, we removed all the structural words like articles or punctuation, and we lemmatized the text. In the sense, all the plural words we put in a singular form, all the verbs in their infinitive form, so that we have what we thought to be pages defined as a set of interpretants. Articles, every word has its part that is structural and content, but articles are very structural, and usually when you go to measure the semantic flow, they just create noise. So we just remove things we thought we...
Did you use the log normal fit because it looks correct, or because you have actually some explanation for that?
Well, about the log normal fit it's you can create a model that gives you a log normal fit. For basically, it's log normal distributions are quite normal in the text analysis. In the sense, for instance, also the length of the sentences of a text is log normal. This originally is a double log normal. It has a double peak, but this is the redirection pages, so we removed it. But yeah, it's just to show you the distribution. It's not important for what is going to follow. Well, what we do is to measure the semantic flow between all the pairs of the 2 million pages. It took a long time. Then what we have is a complete network, of course. What we do is to order the pairs of pages for increasing order of their semantic distance. So the first links to form are the strongest in a semantic way. And so you have a growing network that you can analyze different thresholds. This is the first 500 pages, for instance. So I don't know if it is clear what we did. We measured the semantic flow between all the pages, all the pairs of pages, and then we ordered them for growing value of the semantic distance. So the first links to appear are the ones that are very much connected, and then are very close, so are very similar pages, and then going on, they are always more distant. Those are the first 500 pages of this network, for instance, and we already can tell something. In what we see, this is a disconnected network, of course, but what we see is that semantic areas begin to form. Here we got Ukrainian cities, here we got Spanish cities, Italian cities. The seventh cluster...
Those are 500 pages.
Yeah.
How do you select these 500 pages?
The first, because we created this network, this growing network, and we begin to analyze it at different thresholds, you know? So those are the first 500 pages for how strong is the connection. So the strongest connections come before, and then the other come. So those are the strongest connections of the Wikipedia. I hope this point is clear because it's quite relevant.
And so you increase the threshold of the variable until you get 500 pages. That's what you're doing.
Yeah, this is we are at the threshold where
They
there
are
are.
in clusters. They are divided in small clusters. This is why you have these small things.
Exactly. The first 500 pages, the first clusters emerge. The first cluster represents semantic areas, and they have well-defined semantic areas. They are not mixed. Those are geographical places. For instance, this one is a group of Polish locomotives. The 11th are Chadic languages. The 12th are baseball players. So there are different clusters. These, as you see, they are very well connected between each other inside of the cluster. They are nearly fully connected network for each clusters. And this trend goes on. This is for 1,000 pages. We have Spanish city, American cities, Italian cities, again Spanish, Ukrainian, that is the cluster before, and then other clusters. And goes on, this is for 5,000 pages. More or less, the shape goes on like that. At a certain point, going on analyzing letting this threshold grow, so increasing the network size, the network arrives to a percolation. There is a phase transition. What does it?
Can you explain why these thing changes when you go from 500 to 1,000?
Oh, it's the number of pages changing. So 500 are the number of pages we have at this threshold. And it has this structure. This is just a page representation of the network for the 500 pages. Then, of course, after 500 pages more, there are more pages inside, and other clusters form, and so on. And so on.
What does the correction mean? I mean, you have several structures which are only a single line, but some of them point upwards, some of them more to the right.
Sorry?
If you go back one slide. You know, here the lowest line seems to be similar like the fifth lowest line from the bottom, but they have different direction.
No, it's just a random displacement. It's not. Those are pages, and this link is a semantic link. Just that, of course, you find this is a mistake because, of course, you find only pages that are coupled. I mean, to enter in the network, the pages have to be two pages at least have to be connected. Anyway, this trend goes on until the system is a percolation. What does it mean? In the sense, here we have semantic areas that are well defined, but of course there are correlations between those clusters. There is the Zipf's law, as we all know. So at a certain point, the correlations between clusters become strong and makes the system percolate, makes the system have a phase transition. And we thought that that was a good moment to study the system, to see what happens there. And we found very interesting things. We have the percolation threshold happens when we have 360,000 pages. And the percolation threshold, well, what happens at the percolation threshold? Basically, we have a giant component forming, and this changes the physics of the system. At the percolation threshold, we have a 44,500 clusters disconnected, and the distribution of the size of the clusters is scale-free with this exponent. Now, some of you already pointed out that this is an effect of the phase transition in a network, but this is not true. Because the percolation threshold growing network have a slow at the percolation threshold of the clusters, that is at -3 with a logarithmic correction. Non-growing network have a characteristic slope of 2.5. So this is a really peculiarity of the system. And what does it mean? At this level, every single cluster is a semantic area. So as we saw, there are semantic clusters of cities, there are semantic clusters of guitars, there are semantic clusters of bicycles, languages, people, whatever. And what we see is there is a hierarchy in the on the size of semantic cluster. And this, I think, is an interesting result. The largest cluster here is of around 60,000 pages and is the merging of the two big, very large clusters, and one is the largest American cities and geographical place, and the other one is taxonomies of biological species, from animals to trees and whatever. Apart from that, at the percolation threshold, we can measure also the degree distribution, of course, directional, and we find, again, a scale-free distribution till large scales. After that, it falls very straightly, but the exponent of the degree distribution is very low, and it's very weird for complex systems. I'm going a bit fast because it's very late. Basically, the interesting thing of this exponent is that they found similar exponents in protein interaction networks. So we're talking about a phenomenology that is based on the interaction of entities that are built up of a vocabulary, that is DNA. So in some way, it's a similar phenomenon. We have a DNA on a side, words on the other, organism on the side, Wikipedia pages or concepts on the other side, and we have a similar behavior of interaction at macroscopic level. After that, going a bit fast because it's very late, we measured also the minimum spanning tree. That is a tree percolating all the network. This is not the percolation threshold, but is based on all the network. And we found again a hierarchical structure with a scale-free distribution with this exponent. This is an illustration of the minimum spanning tree around the entry nature, with where the links. Okay, the small balls are the nodes that are the Wikipedia pages, and the links are semantic flows. So, what I wanted to tell you about this figure, and we saw that the semantic space is basically composed in its very flesh by large taxonomies of simple things. I mean, the largest taxonomies are just geographical places or are taxonomies of living species. When you go up to the hierarchy, you find a cluster of more complicated concepts. This thing here, for instance, nature, should be a very important page because it's very general, catches a lot of things. But as you can see, it has degree 4. It connects only with 4 pages, of which one is quite gravitational biology, doesn't exist. So probably it's fake, or does it? I don't know. Well, anyway, but if you go to a level behind, you find, for instance, Earth or ecology that are simpler concepts than nature and are more connected. The moon is more connected, and so it goes on in a scale-free fashion until you arrive to the large taxonomies where the number of connections between pages are very large. And here we can have a break and consider if following with a model, since we have 12 minutes and we are in full digestion, or I don't know, we can stop. You tell me, Ernesto.
12 minutes.
Okay. Well, the model is something that comes out of meta-population systems, this observation of the taxonomies, and in particular, for instance, a reflection about taxonomies that are very much connected. The difference between a taxonomic page and another is on the notation of a few peculiar words. Just an example, Rome is a capital in Europe, Madrid is a capital in Europe, Paris is a capital in Europe. This is a made-up taxonomy of capitals in Europe, where the page, or I mean, how I say it, is exactly the same, just changing one word, Rome, Madrid, Paris. This is the concept from where I basically made up this model. This model can grab the statistical properties of the semantic space at 3 levels of complexity, because it grabs the cluster size distribution, the degree distribution, and the zip flow for the word frequency distribution. Well, so when we generate a new page, this is all here, and those are the words, we basically have a page divided in 2 parts that are not equal. I mean, this is a random parameter, and one part is invariant, and the other part is variable. Nothing more than that. How to generate a new page? We grab some of the words from already written pages. So we grab them from the old encyclopedia, and some of them from a vocabulary of new words. It's fun. To keep the balance between the old and the new words, we use a law of balance that comes out from the IFISC law that tells that the size of the test is a parabola of the size of the vocabulary. So basically, we create a page, we pick some old words, some new words, we make a variant part, an invariant part, and we keep the balance by a law that relates the size to the number of different words, of new words. Well, this is a mechanism of generating a page. Then we have a mechanism of mutation. We have the same page as before. To mutate a page, there is a meaning because we call it invariant and variable part. This part doesn't change. We change just the variable part. How we change it is exactly in the same way. Some words come from already written pages, some words come from a vocabulary of new words. And the balance is kept, the balance is kept by the same law. So we have a way to generate pages, a way to mutate pages. Then the model is very simple. At each time step we generate a new page, and we create an integer number of new pages by copying old pages and mutating them. Well, this model is enough to simulate the cluster size distribution, the degree distribution, and the zip flow for the word frequencies.
What zip flow you put it in?
No, I told you. No, it comes out. I can explain you. I can explain why. Well, I mean, basically, there are. This looks like a very a generative model based on a multiplicative process, because in a sense it is. When we create m new pages by copying old pages and changing them, mutating them, we create taxonomies. So changing this parameter of m, so when we go to measure the space we create, we find clusters of pages given by this mechanism. And changing the parameter of m, we can change the slope of the cluster size distribution. The Hicks law allows us to have a percolation threshold. I mean, this creates, for the fact that we keep words from old pages, creates the chance to create correlations between all the clusters, thus create a percolation, and then we can analyze, and we have also this degree distribution. And well, this was quite a surprise for me to find it out. But it was kind of confirmative for the well, correctness of the model, and those are the conclusions we already talked about. It, and thanks for.
I have a question. Many, I mean, the qualitative notion of complexity is something that is, I mean, on all these quantitative measures, you know, this kind of bell-like curve that you have, the very ordered case, the very disordered, and then in the middle you have the complex. And one of the examples I've seen, I mean, to understand this thing is when they compare, I mean, with some, I mean, I'm not speaking in particular in any measure, but they say a good measure must be able to distinguish a monkey, I mean, typing randomly in a typewriter with El Quixote, for example. Quixote, I mean, that has been something that was different. Well, your model is not exactly this, but what you're doing is like a monkey that is taking El Quixote and then mutating a number of characters, and then you get something that matches the real Wikipedia. So what?
No, well, I mean, it's not a monkey. First of all, second, I would like to point out that the fact that a monkey writer can simulate the zip flow is fake was demonstrated by Ferrari Cancio just recently, I think 2 years ago. I mean, even because the demonstration of Mandelbrot about a monkey writer is about asymptotic, you don't have asymptotic limits in language. But anyway, no, this model is not a monkey writing. If you think about the two basic processes, it's generating a mutation. I can tell you, like copy and replica. I mean, it looks like really a DNA evolution model. DNA duplicate and change some attributes, some genes. It's exactly what it happens with taxonomies, as I told you before. They just duplicate and change some of the words. Of course, there is a complexity in this that is given by the flow. That is by the correlations. Of course, I don't want to say that Wikipedia or an encyclopedia works like that. This model catches some of the statistical properties. And I think it's not that trivial as a monkey writing.
But in DNA, I mean, if your example you mean is faithful to your case, in DNA, I mean, this application that you're mentioning is there are mistakes. I mean, there are some. If I'm understanding understanding correctly what you mean, there's some random mistakes and then originate changes. Here it's the same.
Well, there is nothing exact. It's all random here. But I mean, it doesn't come at this level of description, of course. I mean, there are some parameters that we didn't talk about in the model because we didn't have much time. But also in in this when we change the words, not all are changed, but are changed with a probability. For instance, so there is some stochasticity to create some or to smooth some of the curves coming out of the experiments. But I mean, the parallel I did is very naive with DNA, and I'm not even very knowledge.
When you were wondering why we were laughing here, is because we thought that that was quite a realistic model of how a very prolific scientific author writes papers.
Exactly.
So it would be perhaps nice to compare the results with some author with 500-600 papers.
I completely agree. No?
I was thinking about that just 1 minute ago, but there you have the time, and you have the older papers. I mean, like they are freeze.
Well, yeah, you go create. But that was a comment. My question is, I mean, when you identify these clusters, I understand that there is some form of automatic process to identify these clusters, but then at some point you give a name to the cluster, and that's your subjective decision, right?
You mean when I say they are Ukrainian cities and things like that? No, I mean, there are pages of Wikipedia, so I go there to check and what is this cluster, I check the pages, and they're all Ukrainian cities.
Yeah, but that's a decision you take, that that's what they have in common.
Yeah.
In the case of Ukrainian cities, that's probably an objective decision, but in many other cases, you just assign there a name.
Yeah. I mean, of course.
Whose meaning is something that you have decided.
Yeah.
The point is that the automatic clustering of pages coincides with the meaning one usually gives to the pages. There is an automatic procedure to define clusters. That's it. If you don't look at them, that's it.
Yeah, but
then you can interpret, and this coincides more with what you have in head.
The labeling of the cluster is something that you...
No, it's not necessary to label. Label is just to show you that this is not just a computer exercise.
And also
the label is related to something to do in your brain.
But the label is what gives meaning to the exercise. No?
The point by Paolo, I don't know also but the point by Paolo and others that he cites is that the meaning is the outcome of making clusters.
But then you give a meaning to each cluster. And then you do it in an arbitrary way.
But that's only for presentation purposes. I mean, technically.
Yeah, but the reality is the presentation. That's the meaning of what he has done.
By the way, regarding the presentation, when you were naming some clusters that you were obtaining, you were picking them more or less randomly. So, and some very prominent clusters you were not mentioning what they are. It's not clear what they are.
No. It is It's as I told you. I told you when we wrote the percolation threshold that at that level of semantic distance, the clusters are all well-defined semantic areas. For instance, when I told about the second largest cluster that are taxonomies about biological species. So we're talking about taxonomies of plants and animals. Of course, before there were taxonomies of animals, then plants, and then they merged. But then they merged about taxonomies of biological species. So they're quite. I mean, they're semantic areas. This is interesting also because you can also measure the extent of semantic area, and this is the cluster size distribution what tells you that this extent is scale-free.
So, how do you measure the degree of mutation a patient has had? And when you determine what's enough amount of mutation?
No, I can't. I mean, I didn't measure that. I mean, the model is a toy model.
Because if you are working within a closed set of pages, and that's so somehow you are also swapping from one to the other, and maybe you are just not changing the distributions for this reason.
Oh, sorry.
So you take one page, different pages, and you start to mix things, and then you mutate them.
This is in the model, you mean?
Yeah, in the model. Yeah. So then how you, so how many changes you do, and how you...
Basically, this is just a multiplicative process. So basically, when you pick up randomly a page from the already written pages, it's a modular assignment. So the one you picked up is probable that will be picked up again, and it will be changed in the same variable part. So we'll create a taxonomy always larger.
These pages you take also were obeying the same scale methodology. So somehow maybe you are just swapping things and you preserve the.
Oh, I didn't get it. Sorry.
So that this way of mutating things doesn't alter the distribution of the original data.
No, the original data doesn't exist in the. I mean, the distribution is an outcome of the model. The cluster distribution, the cluster size distribution.
There's one page with a random distribution of words.
Yeah, we start with just a few random pages, and then this whole algorithm. There are no distributions before. The only thing is this keeps flow. That keeps the correlations between the pages. I don't know if you.
Any more questions? If not the case, let's kind of